In this video, we are going to discuss about the wave particle duality. Wave particle duality means it is a hypothesis that depicts that every particle or matter is associated with its own equivalent waves or matter waves. That means we can write every particles or matter, because every particles will have some amount of mass. That's why particles are analogous to matter. So every particle is associated with its own equivalent waves or matter waves. Another part of the wave particle duality is that similarly every waves or traveling waves propagates in the form of stream of particles. And these two statements gives the total wave particle duality. That means if we have a particle like this, suppose this is a particle having mass m. If this particle mass is traveling from position 1 to position 2 at this point, so the mass will be here, mass m. So this particle has traveled throughout the point 1 to point 2. Then according to the wave particle duality, it means that there is an equivalent matter wave associated with this matter, which has traveled also with this matter from point 1 to point 2. This wave is called the matter wave. That means a matter can be thought as an equivalent matter wave. Similarly, if I have a wave which is traveling from some point to another point, suppose this wave is traveling from point A to point B, and this is a traveling wave. It is traveling from point A to point B. So according to the wave particle duality, we can say that this wave can be thought as that stream of particles are moving from point A to point B. This is the simple conclusion of wave particle duality. Now let us take some example. So the first example that I will take is the photoelectric effect. So let us see the photoelectric effect. So to understand the wave particle duality, we need to understand the photoelectric effect. So what is photoelectric effect? Photoelectric effect means, suppose we have there are some types of metal. So if there is a metal, if this is a metal material, let us take a metal. So this is a metal materials. And suppose some frequency of light or some wavelength of light are incidenting on this metal materials. So, according to the photoelectric effect, we can say that there are some particular metals in this world, in the real world, on which some particular frequency or the wavelength, particular frequency or wavelength of light is incident then electron starts to emit out of the metals. This whole phenomenon is called the photoelectric effect. That means if some value of lambda or some value of frequency of light is incident on this metal, then some amount of electrons will start to emit out of the metal due to the incident of the light. So this is called the photoelectric effect, and these electrons are called the photoelectrons. The electrons generated by the light are called photoelectrons. So from the photoelectric effect we can see that there are some particular type of metals in this real world in which if some particular frequency or wavelength of light is incident, then electron starts to emit out of the metal. So for this case, the experiment looks like this. For that, let us take an inert gas chamber. Suppose this is an inert gas chamber, and in this inert gas chamber, let us take a metal plate here. So this is the metal plate that has been connected here, and let us take that particular metal which can emit the light. So this metal is such type of metal which can have the photoelectric effect. So I am writing here, this is the particular metal plate which can show the photoelectric effect. And this is the glass chamber. So you can say this is the glass chamber. Now this glass chamber is full of inert gases. Now let us suppose we are applying some amount of voltage here, and there is an emitter connected at this point. So is the total arrangement of the experiment. Now if we have applied a voltage V, then some amount of current must flow, but the current will not flow because there is no connection between these metal plates. So at the first instant the current will be 0. That means here the value of the current will be 0. Now suppose we incident some amount of light. So we have incident a particular frequency of light. So particular frequency of light has been incidented on this metal plate. So right now what will happen, some amount of electrons will be, photoelectrons will be emitted from the metal plate, and these electrons will be attracted towards this positive metal plate. So there will be flow of electrons like this, and these electrons are generated due to the light. That means they are the photoelectrons. Now suddenly we can see there will be a flow of current of some value, I equals to I1. Before the current value was 0, but when we have incident the light, then due to the photoelectrons, this discontinuity will be not there. Here the current will be taken by these electrons, so we will get some value of current. So this is the proof of the photoelectric effects, that the light after incident on the metal, the metals will emit some electrons, and that electrons will carry the current. So there are some conclusions on this photoelectric effect. The first conclusion that we can draw is the emission of the photoelectron is almost instantaneous. That means emission of photoelectrons will be instantaneous. That means this thing is not explained. This is the instantaneous. At the time when the light incident, at this time the current will start flowing. That is the instantaneous. The second point is that whatever be the intensity of the light, photoelectric effect will not take place if the incident lambda is greater than some particular value of lambda. That value of lambda is called the critical wavelength. So let us assume the critical wavelength as lambda c. So this is the critical wavelength, and this critical wavelength is fixed for every metals. Different metal will have different critical wavelength. Now if the incident light has wavelength of lambda incident, then this lambda incident, if this lambda incident is greater than the lambda c, then whatever may be the intensity of the light, the photoelectric effect will not take place. This is the wavelength called the critical wavelength. The third one is the kinetic energy of the emitted photoelectrons. So we can say that the kinetic energy of the photoelectrons depends on the light. So the kinetic energy of the photoelectron, suppose we can say that if Ek is the kinetic energy of the photoelectrons like this, then Ek, that of maximum, that is the maximum value of the kinetic energy of the photons, will be equals to Hc by lambda minus W, or we can say it is H nu by minus W, where this W value is nothing but the work function of the metal, and Hc by lambda, where c is the speed of light, and lambda is the wavelength of the light incident, and if we say the nu, this nu is the frequency of the light that is incidenting on the metal, and these are the third points is giving the total kinetic energy of the electrons, photoelectrons. Now, the classical physics cannot explain this photoelectron mechanism or photoelectric effect. In 1905, we can say that in 1905, Einstein told that light waves are coming in the form of particles, and these particles are called photons. That means we can think the light waves in the form of particles, and these particles are nothing but the photon particles, and each photon particles has energy E P is equals to H into nu, where nu is the frequency of the light that is incidenting, or we can say H into C by lambda, where C is the speed of the light and lambda is the wavelength of the light. So from this we can find the linear momentum of the photon. So linear momentum of photon particles. Linear momentum of the photon, if we denote it with small p, then it will be E by C, where E is the energy, or EP by C, where EP is the energy of the photons. So we can write H into C divided by lambda into C. If we put the value of EP, it will come out as H by lambda. So the momentum of the photons is H by lambda. So from this example we can see that the light is carrying both the wave nature as well as the particle nature, and this is called the wave particle duality of light. That means any wave, that specifically we can say any traveling wave, can be thought as stream of particles. This is the one part of the wave particle duality. Now let us see, if a wave can be thought as stream of particles, then let us see an example where we can see the particle in analogous wave according to the wave particle duality. So photoelectric effect proves that the light wave which was incidenting on the metal is nothing but a stream of photon particles. Now let us take the second example. So in the second example, we have to take the another hypothesis, that is the de Broglie hypothesis. De Broglie hypothesis. In the de Broglie hypothesis, according to the de Broglie hypothesis, every particle, we can write that every particle or matter, because every particle will have some mass, so it will be a matter. So every particle or matter can behave as a wave, and that wave is called matter wave. So here, according to the de Broglie hypothesis, we can see that any particles or matter can be thought as a wave, and the wave name of the wave will be matter wave. So wavelength of the matter wave, wavelength of the matter wave is denoted by lambda equals to, we have already seen, h by p. We can also write it as h by m into v. So this will be the wavelength of the matter wave, where v is the velocity of the particle. So v will be the velocity of the particle and m is the mass of the particle. So this hypothesis is verified in the later years in an experiment called Davison-Germer experiment. So this hypothesis was verified in the later years using by a pair of scientists. The name of the scientist is Davison-Germer experiment. Very important experiment, but we do not need to understand that experiment to understand what the get syllabus. Just you have to, for your information, I am telling this. Davison-Germer experiment is that experiment which can verify the de Broglie hypothesis. Now, if according to the wave particle duality, we have seen that if we have a matter, suppose this is a matter which has a mass of m, which has a velocity v, and it is moving from point 1 to point 2. So this particle is moving from point 1 to point 2 like this. So according to the wave particle duality, we can say that the matter wave is moving with this particle, and the wavelength of the matter wave is this one, lambda equals to h by p. Similarly, if there is a wave like this, if there is a wave which is moving from some point to another point, then we can say that some particles are associated with this wave, and these particles are moving with the wave. So we can think a wave as a particle or stream of particles. We can think the matter or particle as a traveling wave. So if this is true, then why all the particles wave nature cannot be visualized in this real world? That means, let us the question is right now, why all particles wave nature cannot be visualized in the real world. Means, according to the wave particle duality, any particle can always have their particle nature as well as the wave nature. Suppose if we have an electron, suppose we have an electron and we have a football. Suppose this is a football. Suppose this is a football. This is a football. And this is an electron. So both of them will have some amount of mass. So the mass of the electron is constant 9.1 into 10 to the power minus 31 kg. Similarly, the mass of the football is of the order of generally 0.1 kg. Nearly. We are considering this. Now, the velocity, if the electron moves, so the orbital velocity of the electron is of the order of 10 to the power 6 meter per second. And the velocity of a football, let us consider that it is moving with 20 meter per second. We are considering this value. I am taking an example. So, there are two cases. The first case where the electron is moving, and the second case the football is moving. But we cannot view the wave nature of this football, but we can view the wave nature of this electron. This is the reason, this is the question, why all particles wave nature cannot be visualized in the real world. So, according to the wave particle duality, the de Broglie wavelength of, we can say, the de Broglie wavelength of the electron will be lambda E. I am denoting as lambda E. It will be h by P or h by m into V. So we have the value, and this h is the Planck's constant, that is 6.6 into 10 to the power minus 34 June 7th. This is a Planck's constant. So if we put the value of m we know m is 9.1 into 10 to the power minus 31 kg, and velocity we have taken 10 to the power 6 meter per second. So after putting the value, we will get 725 nanometer, means 725 into 10 to the power minus 9 meter. In the case of football, if we find the de Broglie wavelength, then the lambda will be h by mv. And if we put the value of h, m and v for the football, then we'll have 3.3 into 10 to the power minus 25 nanometer. So we'll get 3.3 into 10 to the power minus 25 into 10 to the power minus 9 meter. So we can see the wavelength of the wave that is associated with the football and also with the electron. Now, in the case of electron, if this is the electron and if the matter wave associated with the electron is this, and this matter wave has a wavelength of 725 nanometer, and this is the football, and this football is also having matter wave associated with it according to the wave particle duality, but the wavelength here is 3.3 into 10 to the power minus 25 nanometer. You can see the two values. If we see the two values and compare, then we can see that the wavelength associated with the football is very much smaller than the wavelength associated with the electron. That's why we cannot detect the wave nature. This very small wavelength cannot be detected by any instrument. We do not have such instrument which can detect such a very small wavelength. That's why we cannot detect the wave nature of the football, because the lambda associated with the electron is very much greater than the lambda associated with the football. This is the reason why the wave nature of every particle cannot be visualized in the real world, but they will have the wave nature according to the wave particle duality. So this is the main concept about the wave particle duality. And last of all, do not forget to subscribe and like our channel to get more videos like this. Thank you.